Hey guys, my name is Adrienne and welcome to Organic Chemistry 2, Part 7 of these recorded sessions. So today we're going over for most of y'all Chapter 19 and in general carboxylic acids and the acidity of the OH bond. So as always, for Organic Chemistry 2, we'll have 20 questions as a review and then a summary. So these sets of questions, or I guess these three upcoming videos, including this one, are going to be pretty one of those things that are really packed. Like we always talk about how, you know, chapters carry over as long as you know the basics, you're good, things like that. But um these are just new, I guess is the best way to describe it. New, kind of like a different way of kind of applying the basics that we did learn or have learned before. So, but there's no problem as long as you hopefully stick around and you know, go to lectures, ask your professors, ask your SI, things like that. You should be good. And once you see, again, it's not too difficult. And these couple videos for actually your upcoming test, because tests are usually 3 chapters each test. So for this upcoming test, um, you'll see how again it becomes repetitive because after this chapter, the next two are pretty much pretty similar, pretty they go together very well, I should say. So that's good, right? Repetitiveness is always good because less things to study and less things to worry about. But again, if you don't get it the first time, then that'll really be bad. Be bad for the second and third upcoming chapters, right? So hopefully you guys pick something up from this video. If anything, the questions are great, right? Manipulate them, do whatever you want with them, however you want to study with them, share them with your friends, tell them to watch the videos, and help you understand it, anything like that. So, with that being said, let's get started. As always, pause the video, take a couple minutes, check your notes, or, just answer them, give me your answer, and we can go through them. Okay, so you're back. We have for one, you guys should have gone what? Carboxy group, you guys should have gone A, or I mean, sorry, B. I didn't see that two there. So B, right? And this is super simple hybridization. We've been doing this since OChem 1 of the carboxy group. Now the thing here is what's the carboxy group, right? And we know it's just this right here, and this is the carbon they're talking about, right? So we're going to be working with a lot of carboxylics, carbonyls, things like that from now on, pretty much. So get familiar. Two, it's asking what two groups make up the carboxylic acid? And I kind of just mentioned it, right? Carbonyls for sure. So, and this OH right here. So two, you guys should have gone B, right? And now again, since it's a new chapter, a new functional group, right? So far, we've encountered a couple functional groups, and each time we had naming, we reviewed their hybridization, things like that. So same thing with carboxylic acids, their functional group, and now they have their own name. They're prioritized, their parent groups, right? So three, you guys should have gone B as well, right? Three, four dimethyl cyclohexane hexane carboxylic acid. So for this one, obviously carboxylic acid is by itself, and then you just name the cyclic or whatever as is, right? As what we've been doing ever before. Um, Same rules, but now this time our parent is carboxylic acid, right? Four, four is also naming, so same thing as well, right? And you guys should have gotten D, dimethyl dimethoxycaproic acid. So as with alkanes, alkenes, things like that. Carboxylic acids has their own, you know, 1 carbon, 2 carbon, 3 carbon type thing, right? We have the methyl, ethyl, things like that. Now for carboxylic acids, it has the same thing. So formic, acetic, propionic acids, things like that. And we'll go over that in the summary so we can write them all down. But you know, don't, don't forget those because those are pretty much the ethyl groups, the butyl groups of carboxylic acids, right? And five, you guys should have gone this one, common name again. And we're kind of going fast because you know the drill with the naming. There's nothing different topic, new same strategies, right? So we do the same strategies. We go through our list, chain, common names, things like that, substituents, lower number, blah blah blah, right? And again, you know, this one you should go and see because this is the common name, right? It still has common names, things like that. So, different chapter, new, different chapter, same concepts, right? So let's move on to the next one. And I think there's more, there's a couple more naming, and then we're going to the colligative properties. So again, right, pause the video, take a couple minutes, assess, answer, take notes, see what you guys get. Okay, so six, you guys should have gone. Again, IUPAC versus common name, they're different, right? So six, you guys should have gone D, right? Pentanoic. So this one, let's do because this one has an ether, right? So we said D for methoxy. So for this one, carboxylic acids are gonna be the priority. We're not gonna number from here. This is your most prioritized when they're in a molecule when you're naming, right? So always this is the first carbon, second, third, fourth, and obviously this one's the substituents, right? We have a four methoxy, right? Which is this one, right? And pentanoic acid. So yeah, nothing too crazy. Six is that it? That's it. Um, Again, now since carboxylic acid is pretty much the top of the priorities for naming and pretty much everything, even acidity, things like that. Now you kind of have to, you know, that can get combined with. You see here, ethyl groups. You can get combined with whatever other groups, right? So be careful with that. Kind of don't, I guess, don't get lost in all the different aspects of it. You know what I mean? So just kind of keep them organized and know that what are the priorities. Priority for sure, number one, carboxylic acids. Okay, seven, again, IPAC structure, and this time with a metal, right? Potassium. So seven, you should have gotten D. So when we name something with a metal, it's always going to be the metal and then the structure by itself, right? So butanoate, it's just another butanoic acid, right? It's the I guess it's the not the parent, but the conjugate of it type thing, right? Eight, arrange the following. So now we're getting to the colligative properties. So, don't ever forget about boiling points, melting points, because honestly, that's probably one of the um, best asked questions, right? Boiling points, melting points, because there's so many functional groups. They have so many different, you know, properties that you can apply. But at the same time, boiling points and melting points, we care about what intermolecular forces, symmetry, surface area, things like that. So still the same concept. And for eight, you guys should have gotten B, right? And this one, again, the stronger the bonds, right? Intermolecular forces, stronger intermolecular forces, increasing boiling point, melting point, whatever, right? And you can see here, one for sure doesn't have anything that doesn't have hydrogen bonds, doesn't have double bonds, so it's definitely the least, right? We can agree. So you should be down to A and B. And now four and two, what's stronger, a double bond or a hydrogen bond? So that's why 4 is, um, you know, the second, and then 2 is the third because 3 has both double bond and hydrogen bond, right? So this is what we're dealing with there. 9, you guys should have gotten D, and same thing. Well, actually, no, this is talking about solubility, but same thing, right? Same concept with colligative properties. Solubility, what's it called? Light dissolves light, right? So, and saying water solubility. So we know that there's the water rule, right? Every hydrogen bond is per, or I guess I should reword this, but every H bond, or I should say one H bond per 5 carbons, right? So obviously, the less the carbons, the better. The more the carbons, the worse solubility, right? And you can see here, D has the longest, has the most carbons, right? One, two, three, four, um, compared to the other ones, compared to two, compared to um, three and one. And then again, 4 and 2, that's why they're the least, is because they don't have the hydrogen bond, right? CH is not a hydrogen bond, right? CH not hydrogen bond. So 3 and 1 is the competing for the top spot, and 1 is the um again most soluble because it's the most polar because it has both double bond and the hydrogen bond, right? And we know water is polar, so H2O is polar. So and then like is always like, right? So more polar, the better. Like there, right? So same concepts, just a different application, just different structures, really. But same bonds, H bonds, double bonds, single bonds. Okay, so let's go into the next page. And 10, of course, ever since we talked about, um, actually, I'll give you a second, pause the video, gather your thoughts. Okay, you're back. So, again, ever since we talked about NMR, spectroscopy, things like that, they've always been in each chapter, right? Because, again, we're going over each different functional group. So, obviously, each functional groups fall on different spectras, right? So, for 10, you should get an A, because why do two noteworthy peaks of carboxylic acids appear in HNMR, right? And OH, very deshielded, right? So lower to 10 to 12, and that's actually like the exact same range it is. And then again for protons of the alpha carbon, which is, what is the alpha carbon? So we have a carboxylic acid, right? Where's the alpha carbon here? Let me add more. So this is the carbonyl carbon, right? Carbonyl. This is the alpha carbon, right? So while this carbonyl carbon does not have any hydrogens, this alpha carbon does, and they're just CsP3s, right? And they're not completely shielded, right? Because they're a little bit in the 2 range, so because they're close to that carbonyl, right? But and that's their exact range as well. And now we get to the good part, right? The good part of reactions. Oh. So 11, what happened here? This one got what? It got added the carbonyl, so it got oxidized, right? So 11, you guys should have gotten D, because out of all of those things, which one of these are the possible um, oxidizers? Again, oxidation, you know, lots of hydrogen, lots of oxygens. So If anything, you guys should be down C and D, but we know C is the famous ozonolysis, right? So it's not gonna make a carbonyl group if it's gonna lyse something, right? So this is officially called oxidation of primary alcohols, which that is, right? Primary alcohol. 12, and this one's a good throwback kind of. And again, like I said, different chapter, but same concepts. We've never seen this type of like structure like in resonance before, right? Or I don't know if you guys have with your professors, but anyways, for the video we didn't like go into this aromatic type thing, right? But anyways, 12, you know, you should have gone D. And why D? So D because even though you don't really need to know what phenoxide anion is, because they're all the same structures here. This is all phenoxide anion, right? But we know in resonance, it's all about stability, right? We care about resonance because of stability. And we're talking about an anion. Anion equals negative charge equals prefers electronegative atoms, right? And which one of those is the most electronegative atom? The oxygen, right? And D has the anion on the oxygen, which is what's preferred for negative charge because electronegative atoms can hold that negative charge better, right? So that's it. We didn't need to know what phenoxide anion was or how to draw it, things like that. But if you just go, you know, remember or recall what you know about resonance, and we even covered resonance this semester, right, with the conjugation, so it's kind of similar. We know that it's all about stability, and we know charges or negative charges like electronegative atoms. So 13, 13 is a little bit, it's kind of tricky in a way that depending on who you have, you may or may not have to know the exact pKa's, right? But as long as you know this like as long as you know this one thing really, you should be good. So 13, you guys should have gotten C because NaH is the strongest base you'll see. So that can deprotonate any acid. So strongest base. So that's a good tidbit, right? Strongest base that you'll mostly see, and that's it. And then it goes from NaH. So the order should be A is less than D is less than B is less than C. So C is that's the order. So A is the weakest base, D is second, B third, C strongest. And again, we you can even look at their conjugate acids as well, right? So, but yeah, just remember NaH is the strongest base, and I'm pretty sure in your notes, or I guess in your PowerPoints in your books, they'll have a list of common bases and their order. But now it depends with your professor if they want to ask you about the exact pKa, right? But again, twist this question to any way you want. You can rank them, do whatever, things like that. So again, study strategies, do what works best for you. But this is a good kind of this might happen, so that kind of thing, right? So you prepared at least. Okay, 14. Rank the following, decreasing acidity. So kind of the same type deal as 13, but instead of bases, it's acidity, right? So, and this one's a good question because you'll be seeing this a lot in the future as well. So 14, you guys should get D. because this is going to come up. Actually, it already has come up. I think last chapter with the withdrawing groups, donating groups. So electron withdrawing groups increase acidity. So the more you have, the more acidic you are, and then vice versa, right? The more electron donating groups decreases acidity, because we know withdrawing groups kind of activate, right? Activate the molecule because then one spot is highly reactive type thing, but then electron donating groups kind of like stabilize everything. Like, okay, we'll give you our zen, you know what I mean? We'll give you our zen to just chill out, don't react, whatever. So, and then obviously the better electronegative, the more electronegative you are, the more acidic, and then vice versa, right? And then um yeah, and then inductive effects as well, right? That sense inductive effects. So inductive effects as well, right? Okay, so remember this here is pretty much all you need with things like this, because a lot of students would kind of instead of using this, the box, the ones in the box right now, they'll think of something like, oh, carboxylic acids um, are all acidic because it has it in their name, and then they kind of get confused, like, wait a second, what's going on, So follow this electron withdrawing groups, and we know, let's see, 4 has actually, let's draw this. 4, does it have withdrawing groups or donating groups? And then here's Cl. So let's do this one real quick, actually, because hopefully we didn't forget our donating groups and withdrawing groups, right? Okay, this one is a what? Electron donating group. This one, withdrawing group. This one, donating group. This one, donating group. So 2 is the only withdrawing group, so that's the most acidic. And then from the rest of them, you can kind of, um, which ones are the most donating. In this case, it's 1 because it's closest to the carbonyl carbon, right? And then these are kind of just getting longer and longer, right? So that's what I mean by inductive effects. Right. So there you have it. So let's go to the next page, and I think the next page is kind of like a similar question. So be prepared. Okay. So kind of same thing. So again, pause the video. Oh, this is the last page. So pause the video, write down your answers, and let's see what you guys got. So 15, rank the following compounds in order of increasing acidity again. You should have gotten C, and again, same thing, right? More electron withdrawing groups, more acidic. So in this case, C3, um, in this case, we're looking at this, right? Electronegativity as well, more acidic. Because now we're just comparing, well, we're comparing Cl, F, and Br, right? Because 1 is definitely going to be the least because it doesn't have any electronegativity, right? So, not too bad, right? Everything's kind of like repeating again. And actually, 16 as well is repeating. Right? The following comments in increasing acidity. So 16, you guys should have gone what? This time, C, right? And why C? So we know C is because basically we're just here to compare 2 and 3, right? So is it a halogen or an NO2 that's more electro withdrawing? electron withdrawing, right? Well, if you think back to that chart we did last chapter, um, the chart where it's like ortho, meta, para, and activator, deactivator. We know that NO2 is way at the top compared to the Cl, which is like at the bottom of the electron withdrawing groups, right? So that's all there is to it. Yeah, definitely remember that. That's a good. You don't even have to memorize it. Just know that the general, I guess, the most common, like for sure, halogens um are here, but everything else at the top is kind of like here. So definitely review that real quick if you haven't already. So 17, physical property, reaction type used by extraction to separate and purify mixtures of compounds. So this is kind of what you do in lab, right? So this might look like, huh? Why? This is like a random question. Well, you just need common sense to kind of figure it out, right? For extraction, what do you need? What do you always do in lab, right? So you guys should get A, right? Solubility for sure, because again, solubility, all about that, the aqueous and the organic layers, right? So that's solubility differences. And then reaction type is acid base, right? So nothing's getting redox or anything like that. Because yeah, let's see. 18. This one's a good one because this one, again, like 17 is like what you do in lab, so it's kind of cool. Like I don't know if this what these are the type of lab questions you guys get in lab, but I think it's kind of cool seeing it in actual, actual question form, I guess. Kind of makes you understand more. Because this, to me, because compared to the labs you guys are doing now, it's much different than what I took. Um, and what I took, I never really, we didn't do these types of things. So for 18, you guys should have gotten C, and why is that? So this is pretty much the trick, right? So the salt is water soluble, right? And the cyclohexanol is organic soluble. Pretty much as long as you know salt is water soluble, you should be good, right? Because C says the salt dissolves in the aqueous layer, which is the water solubility, right? Which is the water. Um, let's see. None of the other ones say the salt dissolves in the aqueous layer. D says it will dissolve in the CH2Cl2, which is organic, right? So pretty much again solubility, right? Like dissolves like. No matter how many different ways they ask you about this solubility, like dissolves like. So organic and organic, aqueous and aqueous, polar and polar, right? Non-polar and non-polar, things like that. That's all you need to know. Um, it doesn't get more complicated than that. 18 is probably the more, I guess, involved or complicated question you'll get because it's such a like there's a lot of different things going on and it's kind of distracting you with all the benzoic acid, cyclohexanol, and CH2Cl2 treated with aqueous and OH. Right? All you really need to know is that salt is water soluble and that everything else falls into place, right? So 19 and 20 I'm gonna do together because 19 you guys should have gotten A and 20 is C. So this is such a biochem question. You'll see it over and over again in biochem. These are called Zwitter ions, right? But the only thing you really need to know is that when the pH is less than equal to 2, pH is around 6, pH is greater than or less than or equal to 10. So, and these are for amino acids, right? For any amino acid. Amino acids. So, this one's +1, this one's 0, this one's -1. And why is that? Because we know pH is all about hydrogens, right? So, if it's super acidic, it has a lot of hydrogen. So that's, we've just put +1, right? +1 meaning the hydrogen. If it's super basic, it doesn't have a lot of hydrogens. So that means it doesn't have that many hydrogens, so it's like -1. At 6, at around 6, it's like no one cares. It's okay, you're there, right? So we went through this question bank pretty quickly, I think. So that's all I have. And now let's get to the summary. So let me get out of this. And first things first, obviously carboxylic acids. Carboxylic acids. So obviously this is their structure, right? OH, R group. And then we have the IUPAC, right? So let's go with naming first. Obviously oic acids. PAC, oic acid. And these are the common names. So these are your like isopropyl, but with carboxylic acids, right? So let me see. There's a total 1, 2, 3, 4, 5, 6, 7. Let's see if they all fit here, right? We have formic or formate or whatever, right? Depending on if it's a substituent or the what's it called, the parent, right? And then we have here acet, so it's your acetic acid, right, or acetoate, and then you just keep adding carbons pretty much, right? Propio, and it kind of almost not really follow the like ethyl butyl pentyl type thing, but not really. So this is butyric, right? Then let's see, 2, 3, 4. We have valeric, and then we have capro, right? Okay, capro, and then of course we have benzoic, benzo, right? So you kind of notice the way I kind of remember this is like 1 carbon, right? 2 carbon, 3 propio, right? Propanol, propane, 3 carbons, butyr, butane, right? 4 carbons, and then Valer is kind of like where it kind of gets weird, but B, 5, right? And then Capro, 6. So things like that. That's how I remember it. Formate, acidic, propio, butyr, valeric, capro, and how many carbons they have. Um, so yeah, count, and you include the carbons, the carbonyl carbon, I should say, right? Let me actually label that right. Carbonyl carbon. So you guys don't get confused. Carbonyl carbon, carbonyl carbon. So, right. So there's the common name, um, and you'll use them. Okay. And next page, more names. I guess more common names. So we're still talking about carboxylic acids. We'll be talking about them pretty much this entire thing, but and again, we're introduced to diacids and salts. right? Diacid, we did a question on this, I think. OH, HO. We have oxalic, right? And we have um, malonic. Oops, okay. Malonic. And then last one. And again, this is just they're adding carbons in between, right? Succinic. So this, there's no carbons. This has one in between. This has two in between, right? And now for salts, we named one. So here, name the metal plus parent chain, and then ending with 8, right? So potassium malonate, right, or something like that. Potassium butanate, right? So kind of just a little bit of info, right? Okay, so now let's move on to nucleic acids. So like always, we don't always start with carboxylic acids. We have to prepare them. So, it requires an initial reaction to get to the carboxylic acid and then the actual reaction to happen, right? Preparation of carboxylic. So how do we prepare carboxylic acid? So one, we have oxidation of primary alcohol, and we did this earlier, right? Using, I'm just going to do this. I'm not going to draw them because we know what a primary alcohol looks like, right? So K2Cr2O7 with H2SO4 and H2O, right? So that's what we're using. Oxidation of primary alcohol. Two, lots of oxidation here because pretty much we're adding the carbonyl and the OH, right? So a lot of oxygens. Oxidation of alkylbenzene, benzene, and this one is just KMNO4. So we're familiar with these, KMNO4, things like that. Yeah. So in this one, this is a special one because the alkylbenzene, you must have a hydrogen in there somewhere, right? So alkylbenzene, something like this, 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 right? They all of these have hydrogens, but this one, it doesn't have a hydrogen here, right? So this is a no-no, right? So must have hydrogen. Three. Ooh, I think I have. Yeah, I should have enough room. Oxidative cleavage of alkynes. So we're starting this time alkynes, right? Triple bonds. And this time we know what's gonna be cleaving it. O3, right? Ozone. O3H2O, right? And as I don't know why they didn't call this ozonolysis. This is what they have it in the book, the notes and everything, but pretty much just ozonolysis. So we know what ozonolysis does. It cleaves, right? If it cleaves the triple bond, we know it'll make carboxylic acids. Um, and actually, here I'm gonna put if it's an internal alkyne, internal you'll get um, 2 RCOH, right? 2 carboxylic acids. If it's terminal, it was 1 plus CO2, right? So same thing. We've seen this a lot. We've seen a lot of ozone lysis a lot, right? So it's good because, we just need to see it one more time and we're good. We don't have to worry about too much about it. Okay, so now to the good part. Um, acidity of OH. Well, yeah, I guess it's a good part because it's pretty. We know what makes it acidic, right? Acidity of OH readily cleaved. Let me put this down with base and bronzidylate acid, or I should say base because it's a bronzidylate acid. So let me take off this dash or slash and put a comma instead because it's a bronzidylate acid. So the OH is a bronzidylate acid. That's what I'm saying. Acts there. Acts as Bl acid. Okay. So now why, right? Because we know the carbonyl oxygen is resonance stabilized, right? Because of that pi bond, because the pi bond can go anywhere. And again, deprotonation by bases. So yeah, it can get deprotonated by bases, which is what we said earlier, readily cleaved with base. So OH, again, you can do a lot of things with that. Okay, and let me put this here so it's not confused with the alcohol oxygen. So again, with the common bases, right? NaH is the best one, and pretty much, let me see here. Common bases. This is what you'll see. Minus is the least, and then you have NH3, which is ammonia, right? Na2CO3, Na plus O, CH3, OH, Na plus O, CH3, right? And then the best one is your Na plus H minus, right? So this is what you, pretty much what all the bases you'll see with OH. Um, there's not a lot of like reactions with it until later, I should say, because we're not gonna get really into that. Or actually, not at all, because this is in this chapter we mostly focused on acidity and focused on preparing carboxylic acids and things like that. So nothing too crazy. But the best part with this, or I guess the most acidity of OH, the most relevant part that we want to know about is this. So common organic acids, right? And this is kind of going to be really weird if you think about it, but ethanol is going to be less acidic than phenol, right? And less acidic than acetic acid. And this is because anything that stabilizes, and again, this is gonna where the conjugates come in, right? So don't ever forget about conjugates, especially when you're dealing with acids and bases. Conjugates are conjugates and their non-conjugates, I guess, come in a package deal. Stabilize a conjugate base, aka acid with a negative charge, right? Makes the acid, which is HA, right, more acidic. So this is because of resonance, right? Resonance stabilizes it. And we know with conjugates, there's always that resonance stability because of that ion charge, especially with pi bonds everywhere. You can just resonate or conjugate or things like that because it's resonance stabilized. Resonance stabilized, right? So now we have the inductive effects. Again, more electron withdrawing groups, more acidic, and vice versa. And I'm not going to put the other one, the drawing groups, because it's pretty much the same. Because this one is pretty much the opposite of what this one would be. So electron drawing groups increase acidity because it stabilizes. Electron withdrawing group stabilizes, um, and stabilize conjugate base and deactivates, right? Deactivate. So if you're stable, you're deactivated, right? And this is we saw this. It's pretty much all the acidic questions in the review, and I think I don't know if I said that they activate or deactivate electron withdrawing groups, activate or deactivate, but yeah, this is electron withdrawing groups deactivate. So sorry if I made that flip flop, but yeah, electron withdrawing groups deactivate because they stabilize. So I think I did that. I switched those two, but yeah, and then obviously opposite for electron donating groups, they destabilize and they activate. Okay, now with the extraction, organic extraction, and this one doesn't really have too much in it, but it's worth a mention, I guess. So you can have an organic extraction with benzoic acid and salt, which is what we talked about earlier, and benzoic acid, and I'm just going to put them under here, right? Organic, and this is what aqueous, right? So between benzoic acid and salt, the salt is the aqueous part. Now benzoic acid and cyclohexanol, again, organic. Cyclohexanol is also organic. So in this case, they're just gonna stop dissolving each other. So what gives? What do we need to do? So in this case, the difference in acidity. Difference in acidity can be used for extraction. So NaOH comes in, used to deprotonate benzoic acid, right? So I'm going to put benzoic acid here, Ba for benzoic acid, making it water soluble. So that's with cyclohexanol, right? And yeah, so that's why. Okay, so That's all for organic extraction. Kind of pay attention to the salts and the cyclohexanol. So depending on which one's used, right? And also NaOH. Okay. So last but not least, oh my gosh, last but not least, amino acids, right? The last two questions we did in the review. It's because of the Zutter ion, and this is pretty much like the first thing you'll learn in biochem. So it's good because biochem one anyway is a lot of OChem. So biochem is one of those classes that will really like kind of kill you if you don't stay on top of it. So this is kind of like a preview or like a little sneak peek of it. So Zutter ions are both an acid and a base because of their charges, right? Because depending on what um, environment they're in, they can be an acid or they can be base. So and they exist as salts. Salts are charged. Okay, so and they also have high melting point and water soluble, right? Because they're salts. Okay, and again, pH is greater than or equal to 10, about 6 or less than or equal to 2. The charge is -1, 0, +1, right? Okay, and that's pretty much it. That's pretty much it with amino acids, and also kind of going further into it. Depending on your professor, you might get into it or not. And actually, amino acids in general, I don't. Depending on your professor, you might get through amino acids or scratch it altogether, right? But there's another word is isoelectric point, which is pretty much pH in neutral form, right? And this is definitely not like you won't cover this in OChem, but it's definitely going to be in biochem. And just to kind of preview it, this is a good vocabulary, kind of like pretty much just saying amino acids. What pH would an amino acid be um, to be in neutral form, right? So we said it's around 6. So isoelectric point is like that precise number. Is it 6.5? Is it 7? Is it 6.2? Right? Things like that. So isoelectric point is like the actual number, right? So with that being said, that's all I have for you guys for this chapter. Hopefully that helped. Very kind of fast. I felt like. Hopefully that felt the same for you. But hopefully you learned something. Again, if anything, you have the questions to work on, right? If anything, hopefully you guys are collecting these questions to get ready for the final, which is perfect, right? Um, yeah, if you have any questions, definitely ask your professors, ask your SI. If they ask you where these questions came from, tell them they might tell them from this video. I don't know. And if you really don't understand, check out my explanation and see. But if you don't really understand, then I'm sorry. I'm sorry. If my explanation didn't like grab your you know, I guess your thinking. But that's all I have for you guys. Thank you for watching, and I hope to see you guys next time.